Greetings, my dear friends. Today I'm going to tell you about quite famous material in the modern semiconductor physics. It's called TMDC. The material is quite noticeable because it consists only of a few layers of atoms, and therefore it's called two-dimensional material. It means the electrons and holes in this material can propagate only within the sheet of material and cannot basically move within the direction where there are a few atoms. And even though the material is so thick, it is so optically active. So from this very layer of atoms, you can get absorption of roughly 20%, which is basically blowing my mind. Let's say solar cell has efficiency of 20-30%, and here you have the similar result of roughly a few layers of atoms. The first famous 2D material was graphene. The Nobel Prize for graphene research was given in 2010, and nowadays it's even somehow in use. For example, you can find graphene-based batteries which are already in the market. And this configuration of carbon, which consists only of one layer of atoms, has unique properties. For example, it has super high conductivity. The research of 2D materials wasn't stopped at 2010, and now we have a new, very noticeable material. It's TMDC. TMDC is structurally similar to graphene because it consists only of a few layers of atoms. TMDC means transitional metal dichalcogenide. The material has attracted so many attention because of two reasons. First of all, it's very optically active. Only from one layer of atoms you can get a really bright light source. The second point is a bit more tricky. It's about the quantum properties of the material. Some quantum phenomena we can observe in the semiconductors usually at very low temperature. It must be 4 Kelvin, 70 Kelvin or something like that. But this material shows us those at even room temperature. Not as good as it would be at the low, but you still can see those quantum phenomena at room temperature, which is very noticeable. And surely the phenomena which we could see in some material only at temperature of 4 Kelvin, in this material we can see at more reasonable temperatures, for example 40 Kelvin, which already brings us to some applicability. This material is bright, optically active material which shows quantum properties at higher temperature than competitors. The material is called transitional metal dichalcogenide, but what is the exact compound of the material? It depends. At least I have mostly seen as transitional metal wolfram or molybdenum, and as a chalcogenide I mostly have seen selene or sulfur. Independently on compound, the material have more or less the similar properties, but the color of the light they do emit depends on the exact compound. Usually it lays in range from 7 to 900 nanometers. It's basically from the really red to infrared. Quite noticeable away, how do people form such material? There is an atomically thin version of this material, for example wolfram diselenide. But there is a bulk crystal, huge, and then you have some special surface which is supposed to be adhesive for this material. Then you attach this, and then at certain condition you can exfoliate a flake. Surely when we speak about material we say something like sheet, but the sheet can be basically grown using some advanced technique as epitaxy or something like that, but for the lab purposes we do not have such facilities, and we can easily exfoliate this material from the bulk crystal. You just attach it to some substrate, then you keep the proper temperature, proper humidity and so on, then you kinda shake a bit and remove, and some flakes remain. When we do so, on the substrate remain some flakes. The flake usually has size of 10, 50, 20, 30 nanometers. Some people can achieve even bigger size of flake, but it's already challenging. But basically, for nanotechnology, if you have some structure of size, let's say tenths of micron, it's already quite huge. For example, the quantum dots I'm working with, they have size of, let's say, way sub-micron, and even nanostructures which we do construct around them have size of, let's say, 3-5 microns, and here flake of size 20 or 50 microns, which is already quite huge. So in the lab we study flakes, but I believe if market is really interested in production of such material, it's possible to grow using epitaxy or something similar, as it was for graphene. Another interesting application is that you can overlay one flake by another flake, and then you have bi or multi-layer structure. The simplest way is to overlay the material by exactly that material, and then the interesting physics kicks in. The flake itself consists of periodic structure, and if you overlay one periodic structure by another periodic structure, and if you even tilt it a bit, tiny one relative to another one, you will have Moire pattern. The Moire pattern ends up with a variation of the band gap within this B layer, and it can allow you to localize some carrier, some electron or some hole in this variation of the potential. It is basically working as quantum dot in the atomically thin layer. If you use multi-layers, you can construct quite tricky structures. For example, they can be used as single photon sensor. That is just an example, because it's not a material itself, it's a playground, and based on those flakes you can construct quite complicated devices, which moreover can keep this quantum property up to quite high temperature and which will remain really optically active. That makes this material really attractive for modern semiconductor physics. There are many conferences where people discuss properties of this material and figure out how can it be applied. If you look to the major scientific journal, you will see how many papers do people publish about this material. It shows that it's really of high interest and it's about to be somehow applied. Now people not only study fundamental properties of the material as it was some years ago, people already speak how this material can be really used. For example, a potential application is single photon detector, is some laser which has size of a few microns. Surely people who work in the lab, they do not really think about the economical properties of the device. They only propose concept. But if the device cannot be produced cheap today, it does not mean it will not be able to be produced cheap tomorrow. So, TMDC is transitional metal dichalcogenide. It's atomically thin layer of this material. Its advantage, because it is very optically active, and secondary, it keeps some quantum properties at the temperature when the competitors already cannot show them. Of those flakes you can construct some devices, as for example nanolaser or sensor of the single photons. And please do not forget to like this video, it's very important for me because I guess it's one of my first videos. Don't forget to subscribe and see you in the next videos.